Mr. Chairman, ladies and gentlemen, I'm second time about fatigue of aluminium alloy, but now about welding. So also it's cooperation with body company, and Sebastian Skrobacz is my PhD student, and other co-authors from our university. The fatigue life under cyclic bending condition of welding joints made of 60-60 aluminium alloy with various welding technologies. The scope of the presentation, as you see, welded door system, fatigue testing of aluminium alloy 60-60 in T6 and T64 statement, comparison of fatigue test result for cyclic bending of samples of unknowledge, no welding. We've seen in the first presentation some part of this, manual welding, automatically welding, crack topography of welding joints, and conclusion. We know that earlier these doors was made by manual welded, but now in the factory is improved automatically welding, and it is very important to see how it influence on the fatigue strength. Of course, it's faster. You may do more in one day, but it's necessary to see how it influences on fatigue. This door system, we look some part of this. This is, we see doors in the middle, and we take spacement directly from the profile used in these doors. So you see on the right hand, for this aluminium, profile of T6 aluminium and profile of T64. And this every spacement will be directly from these parts, not from the factory, but directly from this. It's very important to using in the factories. Now we have seen the same stand, and on the right hand we have the upper, the spacement without notch. We taught this area, and down we make a spacement, welding spacement. How we use this spacement, how this works, I don't know, sure. It doesn't work how this works. But here we have, we may say, we use the mixed system welding, manual welding, and automatic welding. Every time we use 25 spacement for fatigue test. We prepared 2 sheets, was welding, and after welding, we cutting spacement. As we see on the right hand, it is photos of similar spacement. It depends how it looks, with aluminium, manual or automatically. We obtain several kinds of aluminium spacement, welding spacement. Okay. After prepare spacement, it was measurement hardness. Here we have photos of the hardness. So we did measurement hardness every 1 millimeter in points. It was measurement of hardness, many spacement, but on the end we put mean value of hardness. So upper we have robotic welding, green points, and violet probably color, manual welding of T6 aluminium. We see that in region of welding we obtain less hardness compared to the base aluminium. For the steel, usually in the welding region, we hardness increase, but in this aluminium alloy, the hardness decreases. But for aluminium T64, it's nearly the same. Sometimes also a little go down in the welding regime. So we see that aluminium alloy, it's now as in the steel. We see on upper photos typical welding cracks. The beginning of the welding fracture is in the root, but sometimes, not often, maybe 10% of welding spacement, of every hour spacement, the fracture was made in the middle. Why? I don't know. It is true after experiment. And next, we calculated for every spacement this area to calculate the stress. So B, it was always the same, 12 millimeters, 0.6, and first higher millimeter, it was the same. By second, in every welding spacement, it was necessary to measurement, because after welding, we obtain many kinds of these diameters. And on these photos, we have compare on the left side fatigue characteristic, basking characteristic in T6 condition, on the right hand T64. Upper, we have unnotched spacement and characteristics of this unnotched spacement, and down we put spacement of welding joint. The circle is manual, the squares is automatic weldings. Everything black, but we put on this time two characteristics, but these two characteristics is the same characteristic. It is very interesting. It's nearly the same. We see that it's nearly the same. We see also that the parameter is characteristic as nearly parallel, but it is very important that for manual, the coefficient square R is less compared to the automatic. Also for T6 condition and for T64. For automatic, it's larger, 0.88, 0.87. It is very important because characteristic is made for 50% of accuracy. For the engineering, we must move to, for example, 97.5 is such standard, because the coefficient is bigger, so it's no so danger as for manual. So automatic welding, we see that is better because of R square coefficient. If you calculate it for 10⁶ number of cycles, unknown and manual, that we see this coefficient, fatigue coefficient, is 2.0.5, 2.00, for T64, 1.96, coefficient 2.04. So generally, for welding spacements, the fatigue characteristic is moved nearly 2 times down. So I come back. So we see this coefficient is nearly 2. And on the 2 slides, we present photos of several moments of spacement. On the on the left side, it's bigger amplitude of moment. On the right, have smaller. The same here. On the fracture prime, you have morphology of this welding spacement. The same was made for aluminum 60 in T64 treatment, and also we have photos for bigger and smaller amplitude of using moment. And on the end, some conclusion. The obtained fatigue characteristic of non-node samples and the welding joints are practically parallel. Fatigue characteristic for manual welding and automatic welding are the same. The results of fatigue tests for manual welding have much greater dispersion than for automatic welding. It is very important. For all tests, the fatigue notch factor can be determined to be 2. The topography of fatigue crack surface shows similar morphology in the weld area for both welding types. The observed fracture were characterized by a ductile fracture bend. Thank you for your attention.